exothermic and endothermic reactions are both examples of kinds of chemical reaction which transfer energy into and out of them from or to the surroundings. And that can be heat energy, and it usually is, or it can be other kinds of energy as well, such as light energy. The exothermic reaction, the easiest way to tell that it's an exothermic reaction is by measuring the temperature, and if the temperature goes up, that is an exothermic reaction. If the temperature goes down, that is an endothermic reaction. One thing students often get confused about is what you are measuring is the temperature and the energy contained within the surroundings, not within the chemicals themselves. Because when an exothermic reaction takes place and energy is released from the chemicals, it makes the temperature go up. So the amount of energy that is inside the chemical goes down. So I'll just repeat that. In an exothermic reaction, the energy contained in the chemicals goes down because it is released to the surroundings as heat. And the inverse is true as well. When you have an endothermic reaction, it takes energy in. When it takes energy in, that means that it is going to get that energy from somewhere, and it gets that energy from removing it from the surroundings, so the temperature goes down. So the amount of energy in an endothermic reaction, the amount of energy in the chemicals increases, whereas the temperature decreases because the energy in the surrounding mixture has decreased. Students often get that wrong. But in an exothermic reaction, the amount of energy in the products is lower than the amount of energy in the reactants because energy has exited the system, the chemicals. In an endothermic reaction, the amount of energy is higher in the products than it is in the chemical reaction, in the chemicals themselves. That's because the energy has come from the bonds. We can represent those on graphs. These are called energy level diagrams, and they look like this. You can see the one on the left there is the energy level diagram for an exothermic reaction, and the amount of energy in the reactants is higher than the amount of energy in the product. Energy has been released as heat. And the one on the right there is the energy level diagram for an endothermic reaction, and that goes up because it's taken energy in, which makes the temperature goes down. These graphs, notice, are not graphs of temperature. They're graphs of the energy inside of the chemicals. The difference between the energy in the products and the reactants is the overall energy change for the reaction, and that is given the symbol delta H. Delta is a Greek letter which looks like a triangle. So it's triangle H and it's pronounced as delta H. Because delta H, the overall energy change, goes down when you do an exothermic reaction, then when you put a value on this, delta H is negative for exothermic reactions. So if you have a negative delta H, that's an exothermic reaction. Because energy goes up for the endothermic reaction, that is a positive delta H. And delta H for an endothermic reaction is positive. That's a way to tell the difference between the two using numbers. What numbers? Well, when we want to break chemical bonds, we have to put energy in. So bond breaking is endothermic. It takes energy in to break a bond. Put that energy in to break the bond. And whenever we do a chemical reaction, the first thing we have to do is break our chemicals apart. And secondly, if we want to make chemical bonds, that releases energy. Bond making is exothermic. When you do any chemical reaction, you're doing bond breaking and then bond making. So you're putting energy in and then you're getting energy out. And it is the difference between the two that gives us our delta H. So the formula for working out delta H, or the change in energy, is the energy in to break the bonds minus the energy out to make the bonds. Be careful to get those the correct way around. One way to check is this chemical reaction endothermic or exothermic? If it's burning or something like that, it's going to be exothermic. You do the equation, you put your numbers in, and if it comes out negative, then you've done it correctly, or you've at least done it the right way around, because negative tells you it's exothermic. Let's look at a little example. So what we can see here, what we've got, is a table of energies at the bottom here. And That is bond energies in kilojoules per mole. So for example, the first one there tells us that it takes 242 kilojoules per mole to break the chlorine-chlorine bonds. That is a bond between a chlorine and another chlorine. It takes 242 kilojoules to break it. It also gives out 242 kilojoules when it is made. Be aware that that is for the bond, not for the atoms. So for example, if chlorine is stuck to a different kind of atom, like the next one down, where it says carbon chlorine, then that means that we've got 338 kilojoules per mole when we make that bond, or needed to break that bond. So let's see, how do we work this out? Well, firstly, what we have to do is we have to do the energy in. And the energy in, we have to count the bonds. So I've got an HC bond here. I go to my table and I see that the HC bond is 412. I also know that I've got 1, 2, 3, 4. Notice I'm counting the bonds, not the atoms. There's only one atom of carbon. But I've got 4 of those bonds. So it's 4 times that value there, which is 412. So that's how much energy has to go in to break down that molecule there. Then I've got my Cl-Cl bond, and I've only got one of those. So I'm going to add Cl-Cl, gives me 242. So the total energy that I need to put in to break these bonds is 4 times 412 plus 242, which is 1,890 kilojoules per mole. The energy out on the other side here is, again, I look at how many I've got. So I've still got HC bonds, but this time I've only got 1, 2, 3 of them. So this time it's 3 times 412. I've now got this CCl bond, which is 338 if I go look here. So plus 338 plus this HCl bond here, so plus 431. So the total energy out is 3 times 412, 3 times 412 plus 338 plus 431, which gives me 2005 kilojoules per mole. If I want delta H, which I do, delta H, remember, is the energy in minus the energy out. Don't get that the wrong way around. Delta H. So the delta H here, the total change in energy, is the energy in 1,890 minus 2005. So 1890 minus 2005 gives us negative 115. Make sure you get it the right way around, otherwise you'll get the wrong sign. And that tells us that this particular reaction is exothermic because it is negative delta H. So that's how you work this out. Something else that we can represent on a energy level diagram that we saw before is the concept of activation energy. Activation energy is the amount of energy we need to put in to get the chemical reaction started. If two particles just touch each other, they may not react. You've got to put energy in to make them start. A good example of that is if you take a piece of paper which has carbon in it and you just wave it around in the oxygen in the atmosphere, it doesn't react. Whereas if I set fire to it, it starts to react. That's because I've put energy in to start that reaction. I can then take my fire away and my paper will continue to burn. But that's activation energy. That is represented like this on the energy level diagram. Quite often you will get asked to add labels to the energy level diagram. Make sure you get them in the right place. They should only have an arrow on one end, not both ends, and they should go the full way. Delta H is from here to here, from the reactants to the products. It doesn't go all the way to the top. Activation energy is from the reactants to the peak, not from the products to the peak, even in an endothermic reaction or an exothermic reaction. All right, so that is the ideas behind endothermic and exothermic reactions in chemical energetics. Thanks for watching.